A circular shaft of 80 mm diameter is subjected to bending moment of 3 kN meter and a twisting moment of 4 kN meter. If the yield stress of the shaft material is 300 megapascal, determine the factor of safety according to the maximum shear stress theory. Again, you have to use the maximum shear stress theory. According to the maximum shear stress theory, we have tau max absolute is equal to sigma 1 minus sigma 3 by 2 is same as equal to SYT divided by 2 divided by factor of safety, or is simply equal to SYS divided by factor of safety n. So we have a circular shaft here whose diameter D will be equal to 80 mm, is subjected to bending moment M, which is equal to 3 kilonewton meter, is 3 kilonewton meter. So this one is a reaction bending moment. In addition to that, it is subjected to twisting moment also, that equal to T, and our twisting moment is given as 4 kilonewton meter. So this one is a reaction torque. So here two stresses will produce. One is a bending stress will produce, and our value of bending stress is same as equal to 32 times m divided by pi into dq. This one is the maximum possible bending stress, and due to torsion our shear stress is produced. That will be the value of tau xy, and this value of tau xy is 16 times t divided by pi into dq, and the value of sigma y will be equal to 0. So let's calculate here sigma bending first. We have sigma bending is equal to 32 times bending moment is 3 kilo and again meter. So it is 3 into 10 to the power 6 Newton mm divided by pi into dq, and we have given the diameter equal to 80. So it is 80 cube is 59.68 megapascal. This value will assign to sigma x. Similarly, we can calculate tau xy. According to the torsion formula, this value is 16 times t divided by pi into dq. We have 16. We have torque is equal to 4 kilonewton meter. So we have multiplied by 10 to the power 6 divided by pi, and we have diameter is same as 80 cube is equal to is 39.78 megapascal. We have sigma y is 0, sigma x equal to sigma v, and tau xy equal to 39.78. So I will go by the basic principle here. I will calculate first the value of sigma average. Sigma average is same as equal to sigma x plus sigma y divided by 2. Out of that, we have sigma x equal to 59.68 and sigma y is equal to 0 divided by 2. So we get the value of sigma average equal to 29.84. Then the maximum value of the shear, not absolute, this is maximum value of shear is same as radius of Mohr circle, is given as under root of sigma x minus sigma y divided by 2 whole square plus we have tau xy square, that is same as equal to under root of sigma x is equal to 59.78, sigma y is 0 divided by 2 plus we have tau is 39.78 square. So this will give you maximum value of tau max. So we'll get the value of tau max equal to 49.66 megapascal. Using tau max and sigma average, we can calculate two principal stresses, sigma A and sigma B. One time you have to use the positive value, second time you have to use the negative value. We have sigma average is same as equal to 29.84 and we have tau max is equal to 49.66. So we have sigma A is equal to 79.5 megapascal. Similarly, we can calculate sigma B. The second principal stress is sigma average minus tau max. Sigma average equal to 29.84 minus 49.66. So we'll get the second principal stress sigma B is equal to minus 19.82 megapascal. Once you know the stresses sigma A, sigma B, then you have to arrange them in the order sigma 1 greater than sigma 2 greater than sigma 3. So the highest value is 79.5. So in this case we have sigma 1 is equal to 79.5. 19.8 is negative value. So we have sigma 2 is equal to 0 and sigma 3 will be equal to minus 19.82. You have to always arrange this value as sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. And we have given the value of SYT equal to 300. So we can use the formula for tau max and we can find out here the factor of safety. So we have tau max is sigma 1 minus sigma 3 by 2 equal to SYT divided by 2 times of n. So 2 will be get cancelled here and we have sigma 1 value is equal to 79.5 minus 19.82 is equal to SYT is equal to 300 divided by a factor of safety n. Solve this, you will get a factor of safety n is equal to 3.02. Now this procedure is a time consuming technique as far as gate is considered. I will give you one shortcut method. In the torsion, we have developed the concept of equivalent torque and equivalent bending moment if the shaft is subjected to the pure bending and the torsion. So we'll calculate here one equivalent torque T equal to under root of m square plus t square, and this value of T will equate to 16 times T pi dq will give directly the value of tau max absolute, because this equation is based on the maximum shear stress theory. So we have equivalent torque is equal to under root of m square is same as 3 square plus 4 square, 9 plus 16 that equal to 5. So we have 5 kilo Newton meter. Once you get the equivalent torque, in one step you can calculate the value of tau max absolute as 16 times T by pi dq. So we have 16 into equivalent torque is 5 kilo Newton meter is 10 to the power 6 divided by pi, and we have diameter is same as equal to 80 cube. So we'll get the maximum value of the shear stress equal to 49.74 megapascal. Now you can apply the maximum shear stress theory and find out the factor of safety. Tau max absolute is equal to 49.74 is equal to SYT is equal to 300 divided by 2 times of factor of safety, and you will get the same answer of factor of safety equal to 3.02. So for gate, prefer this method as compared to the simple basic procedure. Both methods will give you same answer. This method is little bit lengthy because individually you have to find out all value. So as far as the gate is considered, you have to avoid this. As far as gate is considered, you have to find out the value of T. In one step you will get T. This equation of T is based on the maximum shear stress theory only. This proof we have already done in the chapter torsion. So using T, we can calculate directly the maximum shear stress for circular shaft as 16 times T divided by pi dq, and compare tau max with SYT divided by 2 times factor of safety, and you get the same value. So as far as gate is considered, if the shaft is subjected to bending moment and twisting moment only, then only this formula will work. A shaft of 50 mm diameter is used to transmit the power of 35 kilowatt and 800 rpm. So we know the power and we know the rotational speed, so we can calculate here the torque. For that one, we have power is given as 2 times of pi multiplied by n multiplied by t divided by 60. So this shaft is subjected to twisting moment, and the shaft is supported between the bearing which are 50 cm apart, means the length of the shaft you take as 50 cm. A load of 10 kilonewton is concentrated at the center of the shaft acting vertically. The tensile strength of the shaft is given as 500. Operating factor of safety according to the maximum shear stress theory you have to find out. So consider here a circular shaft of diameter d is equal to 50 mm, and we have given here bearing support at the two ends. The bearing support distance is given as L is equal to 50 cm, that equal to 0.5 meter, and is subjected to load of 10 kN at the center of the shaft. So we have load W is acting equal to 10 kN. Because of the symmetry, we have two reaction and the bending moment will produce. So we have to develop here SFD BMD diagram. In addition to this, the shaft is subjected to uniform torque also. It means that it is a problem of combined bending and the twisting moment, and we have to use the maximum shear stress theory. So we'll identify here the maximum bending moment where it will occur using the SFD and the bending moment diagram. Then we'll calculate the equivalent torque at the critical section, and then we'll using the value of tau max absolute is equal to 16 times T by pi dq. We can calculate the maximum shear, and then we'll apply the maximum shear stress theory to find out the factor of safety. SYT value is given as 500, and because of symmetrical loading we have equal reaction on both end A and B. So in this case we have reaction AY is same as equal to BY. This reaction is same as AY. This reaction is same as equal to BY is equal to W divided by 2. That is, we have 10 divided by 2, which is equal to 5 kN. So first we develop here the shear force diagram, that is SFD. Let's mark the point here ABC. At point A, we have vertical reaction is AY is equal to 5 kN, so we'll move vertically upward by 5 kN. Then there is no force acting between A and C, so the load is remain constant. Then suddenly we have point load equal to 10, so this value is same as equal to 5 kN. We are moving downward where the shear force will change the sign. We have a maximum bending moment. So this value will be same as equal to minus 5 kN, and using the reaction at B will close to 0. Area under the shear force diagram is same as equal to maximum bending moment. So we'll develop the bending moment diagram. Bending moment at point A will be 0. Bending moment at point B will be 0. If you have a rectangle in the shear force diagram, then we have a triangle in the bending moment diagram, and the maximum bending moment will be same as equal to the area of shear force diagram. So this value is 0.5, so it means that we have length equal to 0.25 meter, as well as this length is also equal to 0.25 meter, and this maximum bending moment will occur at point C. So it means that we have C is a critical section as far as the bending stress is considered. So value of bending moment will be same as equal to area of SFD, that is equal to 5 into 0.25 is 1.25 kilo Newton meter. Finally, we'll use here one more diagram, that is a torque diagram, and torque is remain constant over the entire cross section. But first of all, we'll calculate here torque. We have given the power is equal to 35 kilowatt and the rotational speed is 800, so we can substitute for power equal to 35,000, that will be watt, equal to 2 by rotational speed is 800 multiplied by torque divided by 60. So we get a twisting moment T, which is uniform over the entire section, 417.78 Newton meter. This torque is remain constant from B to A, and this value of torque is same as equal to 417.78. So we'll find here the critical section is coming out to be at point C. At point C here we have maximum value of the bending moment as well as the maximum value of twisting moment. So we have equivalent torque is same as equal to under root of m square plus t square. So we have under root of m square. We have 1.25 kilonewton meter is 1250 Newton meter square of it. plus we have torque is 417.78 square of it. Find out the equivalent torque. You will get the equivalent torque is approximately equal to 1318 Newton meter. Using equivalent torque, we are able to calculate the maximum value of shear stress, that is the absolute value, is 16 times TE, which is 1318. It's a Newton meter, so you have to multiply by 10 to the power 3 divided by pi, and we have diameter is equal to 50, so it is 50 cube. Solve this, you will get the absolute value of shear, that come out to be 53.7 is megapascal. And the last step is to use the equation of maximum shear stress, that is tau max absolute is equal to SYT divided by 2 times of factor of safety. Tau max absolute is come out to be 53.7. SYT is given to us is equal to 500 divided by 2 times of factor of safety n. Solve it and you will get a factor of safety is close to is 4.65. So this is a procedure. You have to identify a critical section. Critical section is that section where we have the maximum value of the bending moment and the maximum value of the torque. Bending moment is continuously variable here from A. It will attain the maximum value at C, and then again we have value of bending moment equal to 0 at point B. But as far as the twisting moment is considered, twisting moment is uniform over the entire cross section. So twisting moment plus bending moment, we have equivalent torque is developed, and using this we can calculate tau max, which is to be equated with 16 times of T by pi d cube. Once we know tau max, then we can find out the value of factor of safety. A solid circular shaft of diameter d is subjected to combined bending moment and the torque. This is what we are discussing in the last two numerical. The material property to be used for designing the shaft using the relation is 16 divided by pi d cube into under root of m square plus t square. Under root of m square plus t square is nothing but the equivalent torque. The material property you have to identify whether it is the ultimate tensile strength or tensile yield strength or the torsional yield strength or the endurance strength SE. Now recall here we have equivalent torque is Te is given as under root of m square plus t square, and this equation then become is 16 times T divided by pi d cube. This equation is designed on the basis of maximum shear stress theory. So this value will guarantee you the maximum shear stress but the absolute value, and you have to equate this value with SYS divided by factor of safety. So by maximum shear stress theory, we have tau max absolute is always equal to SYS. So in this case we are using the material property as a torsional yield strength, that is SYS. Choice C is correct. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.